Okay, welcome to another meeting of New England Dynamics and Number Theory Seminar. This week we are in Switzerland, in Zurich, and Alex Gorodnik joins us from there with a talk titled Quantitative Equidistribution and Randomness. Welcome, Alex.
Thank you so much for the invitation. So it's nice to see many old friends. So I'll be talking about joint work with Michael Björklund and Reinhold Fregoli. And I start slowly to give some motivation. So this talk is about Diophantine approximation, and of course what we normally want to see how so if you have a vector alpha in Rd, we want to see how to approximate efficiently this vector alpha by rational vectors. And so the first theorem which answers this question is the Dirichlet theorem. So if we put bound on the denominator, it is known how well vector alpha can be approximated. So this is a given error term, and of course the next natural question is how to improve this bound. And so then the standard definition is the so-called psi approximable vectors in Rd. So we say that vector alpha in Rd is psi approximable if there are infinitely many solutions of this inequality. So we fix a certain error function psi, which normally goes to 0, and we look for approximations pq with error term psi q divided by q. So very natural definition. And then the question is, what can we say about the set of whether the set of psi approximable vectors exists, and what can we say about the set of psi approximable vectors? And there is a very nice answer, at least in measure theoretic sense. So this is Theorem of Hinchin. So of course the answer depends on how fast the function psi goes to 0, but provided that it doesn't go to 0 too fast, and there is actually if and only if condition. So the condition says that the sum has to diverge. So then we will ensure that almost every vector alpha in Rd is psi approximable. Okay, so this is just very basic introduction to Diophantine approximation, but somehow my talk would be about why such a result or similar other results are true, and what underlines this property. And so first of all, so how can we understand Hinchin's theorem better? Yeah, and so in order to understand Hinchin's theorem, we consider these sets of alpha. So basically, we subdivide this problem with respect to Q. And so when I fix Q, I ask whether there exists. So I look on those alpha where the solution of the inequality exists with a given Q. So then naturally the question whether alpha is psi approximable means exactly that alpha belongs to infinitely many of those sets AQ. And then the Hinchin theorem can be reformulated in terms of the sets AQ in the following way. So the set of psi approximable vectors would be exactly this lim sup set of AQ, and we are saying that the set has full measure if and only if the sum of the measure of those sets is infinite. And now if you look on the statement with this new notation, so that really looks like Borel-Cantelli and inverse of the Borel-Cantelli lemma, right? So Borel-Cantelli lemma describes when lim sup set, when the measure of the lim sup set is positive. So here and here we really have both directions. So when can we normally have both directions? The usual situation. So of course it doesn't happen always, but it happens provided that those sets AQ are independent, or sometimes when they are quasi-independent. And so so perhaps the reason that Hinchin theorem is true is, and indeed this is somehow the key of the proof, of at least all proofs of the Hinchin theorem that I know in one way or another involves showing that the sets AQ are quasi-independent in suitable sense. Yeah. So and so that's like one of the examples of arithmetic problem where quasi-independence and randomness plays a crucial role. So so the second part of the warm-up is another classical theorem, which is you can view it as a quantitative refinement of the Hinchin theorem. And so here again we consider vector alpha in Rd, and so we are looking for the same approximation problem as before, but now we are asking not only about existence of solutions, but we are asking about the number of solutions up to Q bounded by capital T. So we consider this counting function, and so then Hinchin theorem is about when this counting function goes to infinity, but naturally it would be nice to have an asymptotic formula for this counting function. And so that was addressed in Schmidt, but in the works of Schmidt. So so here again we are assuming that so this condition that the sum is infinite, and then it turns out that there is almost everywhere asymptotic formula for the counting function. So for almost all alpha, the number of such solution grows like Vt. So the main term is this partial sum of essentially the partial sum of this infinite series, and then so this is the main term, and then the error term, which is approximately square root of the main term. And so, so here again, we see this asymptotic formula. And so if we think about it, this is reminiscent of behavior of sums of independent random variables with so some of those independent random variables so also exhibit similar behavior. And so so we see that NT behaves like sum of independent random variables, and indeed there is underlying independence property which is crucial in the proof of this result. And so so again, in order to show this asymptotic formula, Schmidt establishes certain estimates on these counting functions when Q ranges for, say, in the range 2 to the power I, 2 to the power I plus 1. And it turns out that if we consider this family of functions, they are quasi-independent in a suitable sense, and this ultimately leads, so this is very simplified version of the proof, but somehow that's like one of the crucial steps in the proof of this asymptotic formula. So again, we encounter this kind of randomness situation in deterministic arithmetic problems. And so, so naturally, it's mostly a philosophical question, but what is the source of this quasi-independence phenomena, and somehow how could we somehow systematize these very interesting classical results? And indeed, there is a well, perhaps there are several answers. Probably the answer is not unique, but one answer was discovered by Kleinbock and Margulis, and so it turns out that all these arithmetic problems can be understood from the point of view of dynamics on the space of lattices. And so in particular, they observed that classical Hinchin theorem can be deduced from mixing on the space of lattices. And in fact, this also leads to various generalization of Hinchin theorem in general context. So now I quickly review what do I mean by mixing. So here the key playground, the key space that we work with would be the space of d-dimensional unimodular lattices. So this means covolume 1. And so we can identify the space with the homogeneous space SLDR factor SLDZ. And it is also known that the space supports finite. In fact, we can normalize it. So it's probability invariant measure, which we denote by mu. So this is somehow the main object that we play with today. And so then there is a following result, which so this is called quantitative mixing. And so it says that there exists an exponent delta positive such that for any continuous compact or smooth compactly supported test function phi and psi, and for any translation, so we have function phi and psi, and we have a translation g, and then we consider the correlation of the function psi and the translated function phi composed with g. And so then we are looking on correlation of these two functions, and as g becomes large, then this will converge to the product of the integrals. And in fact, it is also important that one can estimate the error term in this asymptotic formula. So there is some quantitative estimate on how fast it converges to the product of the integrals. And so indeed, this type of estimate tell us that the function phi composed with g and psi are quasi-independent. If we want to apply this type of a result to the setting, classical setting of Diophantine approximation, then the following corollary becomes useful. So, yeah.
Yeah. So in the previous slide, is that norm of G the distance to the identity?
If you want to use a distance or like some Riemannian usual Riemannian distance on the group, then you have to write it in exponential. So it would be like you can also write it as exponential of minus the delta prime distance from G to identity. Yeah. So it's. Yeah, with respect to metric on G, it's actually exponential decay. And here I mean just, for example, Euclidean norm. So you can take Euclidean or maximum norm on the set of matrices.
Yeah, thanks.
Okay, so so in fact, starting with this result about mixing, one can prove other more refined results about behavior of measures. And so a typical result in this direction is the following. So we take AT, so this is say partially hyperbolic subgroup, so say it's diagonalizable, and there are some expanding and contracting eigenvalues, and then we introduce the Gorodnik group. So this is all H's which are contracted by AT as t goes to minus infinity. And okay, maybe I should immediately give you an example. So say the example which arises in classical Diophantine approximation is you take this one parameter group et, e to the minus t normalized so that determinant is 1. So then the Gorodnik subgroup would be this group of upper triangular matrices. And then one also picks a smooth measure sigma, which lives on an orbit of y on the orbit u inside x. So we have basically the following picture. So say we have this leaf an orbit of u inside space of lattices, and then here we have say some smooth probability measure, and then the smooth probability measure is translated by one parameter group AT, and then so typically you get something which is much more complicated, and then the question is how this sequence of measures behaves as t goes to infinity, and so and Kleinbach and Margulis also had this result, which tells us. So in fact, it's a nice corollary of the mixing theorem. So it tells us that as t goes to infinity, this family of probability measure converges to the whole measure on the space. So in fact, this translated things become really very, very complicated and fill the whole space densely. And there is also explicit rate that we have in this asymptotic formula. Okay, so now somehow using these ideas, one can indeed recover the classical results of Hinchin and Schmidt. So I already said Kleinbach and Margulis gave a dynamical explanation for the Hinchin theorem, and Kleinbach, Xi, and Weiss gave a dynamical explanation for Schmidt theorem. And in fact, in the work of Kleinbach, Xi, and Weiss, it was useful to prove a little bit more. I mean, not just the result about behavior of a single translation, but what happens if you take two test functions and two different translations by one parameter subgroup, and so then you have integrals of this form. So you have two smooth compactly supported functions phi1 and phi2, and then we analyze their values on different translations of the measure sigma. So this is like a double correlation, which arises in the proof of the Schmidt theorem. And more generally, of course, it's natural to consider higher order correlations. So higher order correlations are integrals of this type. So when we take R test functions, and we have R representatives in this in our subgroup, and we analyze how the values of these functions are correlated, at least asymptotically. And so this is somehow so understanding properties of this type of integrals would exactly capture the quasi-independence phenomena, which which somehow was in some sense hidden in these two classical results. And so what is known about this type of integrals? Yeah, so I survey some of the known results, and so in particular, starting with the question about mixing. So here, instead of two functions, we consider this integral with R functions. So we have R compactly supported functions, smooth compactly supported functions, which are translated by R different matrices in SLDR. So we have this integral, and what one can say that as under suitable condition, this integral will be approximately equal to the product of the integral. So again, it's this quasi-independence property, and so the error term is controlled by differences between those matrices GI and GJ. So provided that norms of GI, GJ inverse are large, so the matrices are far, so these differences are far from identity, we have a very good understanding of these correlation integrals. And then for the setting where we have the measure on unstable leaf, there are also results. Yeah, in fact, maybe I should also mention Dolgopyat here. Yeah, I think there is also work of Dolgopyat which gives this type of estimate. So there is works of Dolgopyat and Xi. So say if you have this smooth measure supported on unstable leaf and consider the corresponding correlation, then again this will converge to product of the integrals, provided that this error function goes to infinity. So here what we require is that basically all TIs go to infinity, and also the gaps between TIs go to infinity. So this is sufficient to have this asymptotic formula. So now finally I am moving on to the main subject of the talk, and so ultimately what I want to explain today is how to use these correlation formulas, and in fact like these two classical theorems which we saw. So given this quasi-independence quasi-independence estimates on correlations, one should expect that these two classical results are only tip of are only manifestation of quite general phenomena. And so what I want to explore is behavior of Minkowski function. So this has to do with improving Minkowski theorem, and also I want to talk about generalization of Schmidt's result in multiplicative Diophantine approximation. So okay, so first let's talk about Minkowski theorem. So here let us pick a box B. And then we consider, so we assume that this box has volume 2 to the power d, and we also take a lattice lambda with covolume 1. So then, as a special case of Minkowski theorem, one knows that there is always at least one non-zero point inside this box. And so now we ask, okay, so how sharp is Minkowski theorem, so how do we formulate this question precisely? So now I pick a constant c, say smaller than 1, and consider a smaller box c times b, and then I ask, okay, so what is the smallest c for which we still have non-zero lattice points inside this shrunken box, inside this smaller box, and then of course if we ask this question for completely general lattices, there is obvious answer. So given a box, you can always cook up a lattice for which the Minkowski theorem cannot be improved. So, but the lattice somehow is determined by the box. So so if you want to have if you want to have everywhere statement, there is not much we can say. But on the other hand, one can wonder what happens for generic generic lattices. Yeah, whether Minkowski theorem can be improved for generic lattices. And so this leads to the so-called logarithmic law. Before stating it, I introduce notations. So if you have two boxes with coordinates bi and bi prime, so we can measure the distance between those boxes just by comparing the logarithm of bi and bi prime. So then we have this nice distance, and then what one can show. So this is a theorem of Kleinbock and Margulis, that in fact along, so if we consider all so we take a generic lattice B and then consider all possible boxes. So as the size of the box, as somehow the box goes to infinity, in fact, one gets that the Minkowski constant, at least for some collection of boxes, right? We are talking about Lie-Min. So for some collection of boxes, this Minkowski constant becomes, well, the collective, right? Yeah. Yeah, so this Minkowski constant becomes really small. So and then so somehow a more refined question one can ask. So this asymptotic formula suggests somehow that under some perhaps under some normalization of Minkowski constant, we should observe non-trivial distribution. And so so what we so now we sample Minkowski constant over a finite family of boxes, right? So we pick a finite family of boxes, and then I consider the minimum of Minkowski constant over this finite family of boxes. And the question is how this function function m b lambda behaves as I increase the number of boxes. So so we would expect that this function somehow decays with some rate, and then one can consider analogous situation. What happens with independent events that have a small probability. So so here is somehow heuristic model for what we should expect. So let us consider independent events, and we assume that probability that this event happens is lambda divided by L. So as L very large, so the probability of this event is very small. And but of course, if we keep doing this independent samples many times, even so the probability is small, we still would expect to get non-positive probabilities that one of the events occurs. And so then one can show as an exercise in probability that the probability that none of the events A1, AL occurs converges to 1 minus e to the power minus lambda. So that's somehow a basic heuristic, and it turns out that this heuristic also applicable to our setting. And so, but in order to formulate the result, we need to specify over which type of boxes we sample, and so we introduce. So if we have a finite collection of boxes, we define the width of this finite collection. So this is minimum of the distances between B and B prime, where B are different boxes in this collection. So if you sample two boxes which are very close to each other, of course we are not expecting to get any independence. Yeah, so in particular we can kind of sample over some compact region, so that's not very interesting. Okay, and then what we get is the following result, which says, okay, we have a finite collection of boxes as before, and we are assuming that the number of boxes goes to infinity, and also that the gaps between boxes are large, at least on the logarithmic scale of the size of B. So we have these two assumptions, and then it turns out that this function m b lambda grows roughly like cardinality of b to the power minus 1 over d, and we do have non-trivial convergence in distribution. So now if we ask about the measure of the set of lattices where mb lambda smaller than this upper bound, so then this measure will converge to the expression which we expect for which we've seen in the case of independent random variables. So, in fact, one can formulate this theorem a bit more precisely. And so, okay, so I also wanted to mention, so somehow knowing this distribution result, somehow, so it tells us the expected growth of this minimum function, and so this actually can be used to deduce the logarithmic law about Lie-mean of the Minkowski constants, and then one can actually formulate this result more precisely. So now we can also ask, okay, if I'm looking on Minkowski constant for a collection of boxes B, so I can ask how many of those boxes have Minkowski constant smaller than U. Yeah, so this way we actually count the number of those somehow extremal cases that occurs, and then we have also an asymptotic formula for this counting function. So here, if we put the bound, which is xi times the number of boxes to the power minus 1 over d, if you put this bound, then this counting, so this bound is going to shrink as the size of the number of boxes goes to infinity, but what we get that this counting function has a non-trivial distribution, and in fact it converges to the Poisson distribution. So somehow this statistic of rare events, which is typical for Poisson distribution, also happens for the Minkowski constants.
So alpha is lambda here.
Alpha, where did they say? Alpha is lambda. Yes. So this should be lambda. Yes. yeah. So here, yeah, we are sampling overall lattices. Yeah.
I can ask for the definition of W of B. Sorry, I forgot the definition.
So W of B. So okay, go a bit further. So it's W of B. Here.
No, you missed it.
The next.
WB. Sorry, WB. So this is just the minimum of distances between. So we have two boxes, right? And then there is this metric which tells us how far the boxes are apart, and W of B. This is basically tells us the smallest gap between the boxes over which we sample.
Yeah, thank you.
Okay, so okay, so where am I now? Okay, so now I will try to explain a little bit about the proof of the theorem, and in fact the proof is very easy, modulo results about correlations. So here we start with the box B of volume 2 to the power d. And naturally, we can associate to this box the diagonal transformations, transformation AB with coordinates B1, BD, and then two more notations. So now we consider OU. So this is just the cube of size U. And then we define the set of lattices, lambda. So this is set of lattices which don't intersect the cube OU. So this is collection of lattices in X, omega U. And now using this notation, we can say the following. So, so we are interested in the situation where the Minkowski constant is small. So namely, it is smaller than U, but this can be reformulated by saying that lambda intersection. So the box B we can obtain box B times U we can obtain from the cube which is scaled using the diagonal transformation AB. So this is really just a tautology, and then another tautology. So we are saying, okay, this happens. So this means exactly that translates of the lattice lambda by AB inverse lies in the set omega U. So now if we use this notation, so this counting function, so it counts how many times we have a small Minkowski constant can be rewritten as a sum. So we are summing over the boxes, and then here we have characteristic function of omega U, and then we are checking whether this translated lattice lies in omega U or not. So we have this representation of the counting function, and then ultimately we can ask how the moments of the counting functions behave. And if we use the representation from the previous slide, then we can rewrite it in this form. And here, naturally, we have the integrals, these correlations of order R, which we encountered already, and so knowing information about this type of integrals, one can actually gain information about all the moments of the counting function. Yeah, so this is a very brief summary of the argument for Minkowski constant, and now I am moving on to the second application. So here we want to investigate a multiplicative analog of the Schmidt's result. So at the moment it's just in dimension 2. So we fix a vector alpha in dimension 2, and then we also have an interval I, and then we ask. So we are looking on all integral solutions of the following inequality. So we require that the product of Q, P1, Q alpha 1, P2, Q alpha 2. So product of these guys lies inside interval I. And then we are interested in analyzing the following counting function. So this is really just so the number of such QP1 and P2, which additionally satisfies these inequalities. So here R is, so I think, yeah, so we think about R being fixed, but potentially one can take it, grow slowly to infinity, and T goes to infinity. So we look on this basic counting problem. So we're counting integral solutions to this family of inequalities. So how should we address this question here? And so the relevant dynamical system which arises in this problem is the following. So here we consider now a two-parameter group or two-parameter semi-group. So this is two-dimensional group of diagonal matrices, and then we also have the following two-dimensional subgroup of unipotent matrices. So this is somehow a substitute of what we had in the first part of the talk, but the difficulty is that this group is two-parameter, and also this one-dimensional subgroup is not the unstable leaf. So this is not unstable, not a spherical group, or not unstable. Unstable.
Well, it is unstable, yeah. But it's smaller than the whole thing.
Yeah, not the full unstable. Yeah, so it's smaller than the full unstable subgroup. So this actually creates quite some difficulties, and well, actually somehow the situation is much better understood if one is interested in asymptotic formula without error term. Then this was studied, and there are lots of amazing results, starting with the work of Nimisha, which tells us how such objects distribute, and this is somehow fits into general theory of unipotent flows. But in order to prove this probabilistic result, we need to have quantitative estimates. So what is known regarding quantitative estimates? So here, as before, we put a smooth measure on the U orbit, and then here is a quantitative estimate also due to Kleinbock and Margulis, and so it turns out that more or less the same statement is true. So we have this measure sigma. So again, we have some measure sigma on this two-dimensional leaf, and then we are translating by this two-parameter group, and we obtain some complicated measure, which is in the limit becomes equidistributed in the whole space. But here one needs to be careful. One has to say precisely what do we mean that parameter t goes to infinity. And it turns out that the correct condition for this theorem to hold is requiring that both coordinates T1 and T2 go to infinity. And indeed, if only one coordinate goes to infinity, this result wouldn't be correct as stated. So, but this is a natural generalization of the one-dimensional situation, and And then there are other generalizations to more general homogeneous spaces. In particular, there is a result of Xi, which tells us precisely what happens with general correlations. And so here, as before, we have a correlation of order R. So we have this correlation, and then asymptotically this will be equal to the product of the integrals, and one has to specify what do we mean asymptotically, and this is given by the following error function. So namely, we need to assume that floor of T1 is big, and floor of all the differences is big. So this actually quite in some sense quite a natural condition, but somehow if you have say this point T1, so in order for this result to be applicable, the point T2 has to lie in this cone, which is should be like far away, and then you also have to pick subsequent points which lie like in this quadrants far away, and so on. So okay, so but one can still wonder what is the right shape of this error term. And so in particular, if we maybe have 2 points which are far away, but maybe one point is here and another point is say here, T1 and T2. So we have two points in T2. They're far away, but not in the sense of this cone condition. Can we say something? Still say something about this type of integrals? So so this is our technical improvement of the result of Xi. So the statement is essentially identical. The only difference is that it is sufficient to, okay, we still need to know that the floors of each Ti go to infinity, but it is sufficient to know that the distances between Ti go to infinity. Then we do have a quantitative estimate on the correlation. So even so, it is technical, seems to be like a technical improvement, but it is actually crucial for the application which I'm discussing. So and hopefully I will explain why this technical improvement is needed. So so now we go back to the problem about counting the number of integral solutions. So so it's natural to introduce the following notation. So we define the region in R3 just by these inequalities, right? And then given alpha in R2, we introduce a lattice. So this is a lattice in R3 given by this formula. So then the original counting problem can be interpreted as counting lattice points lambda alpha, which lie inside of this region. And so so now what we can show that that there is an analog of Schmidt's theorem. So this is joint work with Björklund and Fregoli, that for almost all vectors alpha in R2 or in 0, 1, 2, when we look on this asymptotic, when we look on the number of solutions, it is asymptotic to the volume of the set, and there is also error function, which is approximately square root of the volume. So we have this asymptotic formula, and then with a refined argument, one can also estimate the variance in this formula. So those are two related results. So basically, we ask how the error term in this asymptotic formula behaves with respect to L2 norm, and it turns out that it grows like log t. And maybe I should also mention that the volume of this region is like log t squared. So here we so here we do have square root. Well, actually, if I do it like this, so what did they say? Yeah, maybe I should also put square here, right? Because this is so log t log. Yeah, so if I write it in terms of L2 norms, then so basically the error term should be like square root of the main term. So okay, so now I can also explain. Okay, I still have a bit of time, so I can explain a bit how these asymptotic formulas can be proved. So the first remark is that this counting function can be represented, can be approximated at least by the following sums. So here we have some functions phi on the space of lattices, and then we have some finite subsets of R2 plus, and then we basically tessellate the regions in a convenient way, so that the original counting function can be represented as this sum. So then, if you want to analyze the L2 norm or L2 norm squared of this function, so we multiply and we multiply this thing out. So then again, what we get in the end is the double sum over n1 and n2. So those are two vectors in R2, and then we have this correlation integrals. Right, so somehow the correlation integrals arise quite naturally in the setting. So the hope is that the asymptotic formulas for those integrals which we have will be useful to analyze what happens, right? So and of course, in order to use this asymptotic formula, so I mean the asymptotic formula don't apply, don't work well for arbitrary n1 and n2. So they would work well provided that floor of n1 is big, floor of n2 is big, and at least the distance between n1 and n2 is big. So then in this range of the sum, we would be able to use the asymptotic formula, but somehow additional challenge is still to analyze these kind of degenerate cases. So the idea is quite simple. We split the sum into three subsums and analyze what happens in each case separately. So that's the idea. Yeah, so here maybe I'll even draw a picture, right? So we have basically right. So we have kind of a generic case, and then we have the case the points on the diagonal, and then there are also points which are close to coordinate axis, right? So basically those are the cases that we have to analyze. And maybe another technical difficulty which arises in the proof is that this function phi, which we use in the computation, are unbounded function on the space of lattices, and so we do need to understand. So when if somehow when we integrate over at lambda alpha, and these points are in the region where the function phi are very big, then we do have a problem. So one needs to control escape of mass. So we need to somehow say that not too much, not such a big proportion of alpha is far away at the cusp. And so ultimately, what we needed to show is the following L2 estimate on those functions. So, which is roughly a non-divergence estimate, and it's yeah. So ultimately, at least. So we have this type of bound. So maybe one thing that you see from this bound is that if the floor of n is large, then we do get a good estimate. But if the floor of n is small, it could even happen that our bound blows up. Right, so the norm could go to infinity, but floor stays bounded. Then we do have a problem, and it seems like that this is indeed what happens with those L2 norms. So there is no uniform control of these norms as we approach coordinate axis. So now I just briefly summarize what happens in the three regions that we are dealing with. So here we have this generic case where all the floors are big, and also the difference between n1 and n2 is big. So this is in fact the main term. So it's asymptotically. So the number of terms in the sum is asymptotic to the total number of terms in the sum. And then indeed in this range, the asymptotic formula for two correlations is crucial, and it gives the good bound. And so if we use this asymptotic formula, we conclude that in fact, even so we are summing over log t to the power 4 terms, the contribution of this sum is negligible. So it's not going to appear in the asymptotic formula. And now what happens in these degenerate cases? So for the first, so the number of degenerate cases is roughly log t square, so it's like roughly square root of the main term. And if we are interested in asymptotic formula with extra log, then we can still use our L2 bound and get an almost everywhere estimate, like in the first theorem. But for the second theorem about variance, so we do need a more precise bound, and these log terms which arise on this boundary regions are actually not satisfactory to get the asymptotic formula. And so then what happens is that one needs to additionally analyze convergence. So there is like additional cancellation which we observe, which happens in these degenerate sums, and it comes from additional equidistribution phenomena. So for example, okay, this is there are like several cases of this type, but like one more or less typical example is the following equidistribution statement. So here we have a double correlation, but we are translating by these degenerate matrices where so we have these two degenerate transformations where one of the coordinates is 0. And then it turns out that we don't get equidistribution with respect to the measure on the whole space, but we do get equidistribution for measures which lives on a smaller collection of lattices. So there are this homogeneous subspaces of lattices y1 and y2, which somehow arise naturally as in the limit, and somehow using this additional asymptotic formulas, one can actually control what happens in these boundary regions. Okay, and so finally we left with analyzing this case where we are next to the diagonal, and so then indeed this is kind of but this is somehow the only part which contributes to the variance. So this diagonal part indeed contributes to the variance, and then one can estimate what happens for the diagonal sum. Okay, so I think I'm okay. So basically, I talked for an hour, so I should stop.
Okay, well, let's give a big round of applause to Alex. So the seminar is an hour and 15 minutes, so which means that
okay.
Roughly an hour is for the talk, and then some time for discussion.
Okay.
So if anybody has any questions, please.
The last thing you did about these two different direction of equidistribution was interesting. This one, it looked
yes, yeah.
Interesting. It looks different than other thing which we saw before.
Yeah. It's kind of curious. Because we kind of struggled to understand what happens. So somehow we had the first argument which kind of gives an upper bound. So how the number of terms which we have to analyze was not really that big, but then you still get this extra log terms, and then somehow we realize that we cannot really get rid of the log terms, but somehow if we rewrite the sum or the sums in the right way, so then we get like differences like we see here, and then ultimately this is somehow this limiting integral would cancel out, and then you get things without log logs.
Yeah, just the type of the result is interesting.
Okay, yeah.
Because it has scope of you can easily see it's So you did only for SL3 and not for higher.
At the moment,
complicated.
I mean, there are some things which, maybe actually this part would be also a bit of a pain to write, and I mean also this non-divergence estimates. So I mean, this correlation estimates are true in general, but for example, where is it? I mean this estimate is also kind of a bit because we do need some good control, and ultimately we kind of have to improve this type of bound from scratch. So it's kind of related to the usual non-divergence estimates, but then somehow what happens, you get some exponent, and somehow it's not good enough for our estimates. So then we had to somehow analyze much more carefully. So it's ultimately it's kind of fits into this general Klein-Margulis non-divergence machinery, but we had to get our hands dirty and do it.
So this is not this Margulis height function kind of thing here, or?
So we had to do it carefully ourselves. Somehow, there are these general things about polynomial C alpha good maps, right? But somehow then you get an estimate which is somehow not sharp enough. So you just get like something, but it wasn't enough for us. So then somehow at the moment we just wrote this in dimension basically for in the space of three-dimensional lattices, right? Like what I am. But maybe something like this should be true in general. Also like this type of estimates, at least for kind of this. so here we have like two intermediate homogeneous spaces which play a role, but then in dimension n, right, it's kind of becomes a bit annoying, but probably it should be similar. Yeah, I would expect it should be similar, but just like there is
looks like there's some kind of a flag or some kind of partially ordered structure of those intermediate guys. But it's
probably in dimension so there would be like a flag of like a tree, I guess, of these different intermediate subspaces, and then probably you still would get some cancellations, but it's somehow so, you still haven't thought about it. I think there could be probably I would expect it should be still true, but one needs to understand somehow the combinatorics better.
I see. Okay, other questions, comments, suggestions?
How is your result different from Ron-Gang-Shi's result? I mean, you have a, so there is some matter of order or something.
So so basically it's I mean the only difference is this. So what do we have to assume about T1 and T2? So okay, here.
Yeah, they are away from each other in certain way, in some order.
So here you have like a linear order, and actually in Rogan argument there is like an inductive statement, because there is like one TR is somehow the biggest one, and or maybe like maybe you start with I guess you start with TR and then you kind of say
go down.
Okay, this is like expands so much, and on this scale the other guys are essentially constant, kind of like this, and then you kind of produce kind of go down, and you ultimately get this the fact that the integral kind of splits. So I guess the point is that somehow the size of TR minus 1 is so small that dilation by somehow any direction by TR would kind of produce you still equidistribution. So that's kind of the thing, and somehow so in our case, right, we are so we only need to know that the distance between TIs are far, so somehow you don't need to have a linear order. So it could be like any collection of points which are like far apart from each other. So
that one was very limited in the scope. This is like geometry is you can do any direction. That's nice.
Exactly. So that's the difference, but ultimately, right, because we are kind of explaining it in the opposite order, because we were thinking about this counting approximations, and then we were trying to use this various asymptotic formula like that one, and then we kind of realized that somehow the range where this formula applies, you really get like lots of points where you cannot apply it, and then so that was kind of our problem, and then we kind of go back and started thinking, okay, can we improve,
so you really need a U orbit to be compact for some reason of the way you argue?
The way how we prove it, at least because let's see how to explain it. Because I mean the idea is to use extra invariance. So if you have a compact U orbit, right, there is a one parameter group which there are actually many one parameter groups which just any one parameter group in U would keep this orbit invariant. And then basically the idea is you introduce extra averaging. So if you apply this averaging along U, so you first average over sigma, but you add extra average over one parameter subgroup to this integral, nothing changes. But then the point is those matrices ATI is going to kind of stretch this one parameter group after conjugation. and then ultimately there is some way to rewrite these integrals, and ultimately we use mixing on the whole space of lattices, where we go in direction of this conjugated one-parameter group. So I mean, it's maybe not so easy to explain all the computation, but like the ingredient which helps is this extra averaging over one-parameter group, and then like after some additional estimates, we use that there is also mixing in this conjugated one-parameter group with respect to the measure on measure mu on x. So that's yeah.
And for going to infinity also you need the same thing, compact U orbit, or you don't need?
For going to infinity,
this cusp estimate for the cusp.
So for cusp estimate, I don't think we use it. So probably it could be still. I mean, okay, so it's kind of arithmetic because we ultimately somehow write explicitly things and like estimate alpha functions, and yeah. So I guess we at least the way we write it, we start with the integral lattice. But maybe it's not so important. Maybe one can start in a different base point. Yeah. So at least the way we've done it, we just started with. Because it's kind of like, I mean, ultimately it's like some arithmetic computation. So okay, yeah.
But this means that the compactness of the orbit is used.
So for non-divergence or for
so for non-divergence, it probably shouldn't be used, but I'm not sure exactly where this compactness of the orbit is needed.
Yeah, so
it will be lost.
Yeah, so here somehow, yeah. So we need like okay in this estimate, right? So we okay. So maybe like the most basic case, if it's really invariant measure on the compact U orbit. So then you do get invariance under one parameter group, and if it's not invariant measure, you can maybe add like some density function, which also can be controlled. So, but somehow if one just starts with some measure on some leaf,
under what?
So we want to have at least one unipotent subgroup such that if we apply this unipotent subgroup to the measure sigma, so this thing, say for example invariant, yeah. So somehow that's the easiest situation, or I mean, yeah, one can also refine it to have a smooth density additionally, but somehow this measure sigma. In our argument, we use that this measure sigma is invariant under something. So like if one starts with just with a measure living on a leaf, so then yeah, I don't know.
I see. So if the leaf is not compact, this of course there exists invariant measure. It's just not finite. And then
yeah, exactly.
Example of this invariant measure.
Yes.
Yeah. So it becomes technically more difficult. Maybe there's
and then somehow it becomes a different, because this so then this one parameter group kind of go. I mean, that doesn't really preserves this measure on the leaf, right? It kind of moves it around. So indeed, it's kind of a different game. Like if you live on a compact leaf, you kind of then you have this extra invariance. So. And this is somehow the main idea in our arguments. So that's for that sense, I don't know, but actually in most applications you do have like in all these arithmetic applications. Yeah. So it's
usually you apply only to this situation. So I think it's very important that you recognize that it helps to assume this. That's nice.
Yeah.
Okay. Well. I guess we ran out of time, and it was a great discussion. So let's thank Alex again by doing something like this. And it was great to see everybody. We still have a few talks this semester, maybe 3 or 4. So I hope to see you guys later, every Thursday. Thanks.
Yeah.
And for those who are not with us, the video will be up there soon, I hope.
Hi, Anders.
Okay, yeah, Anders, good to see you.
Hi.
Okay, bye. Thanks a lot for the invitation. Yeah.
Okay, bye, guys.
Okay.